In this video, we will continue the presentation of analysis of variance. In particular, we will talk about factorial ANOVA. In one-way ANOVA, which we saw in a previous video, we compared means of independent groups using a grouping variable with a number of levels, but we could only have one independent categorical variable. Analysis of variance actually allows us to compare across more than one factor. That means that we can have more than one independent variable, and those can be taken into account simultaneously. We can analyze for the effects of multiple independent variables on the same dependent numeric variable. And this allows us, very importantly, to test for what is called statistical interactions. Statistical interactions, which are also the main reason that we discuss analysis of variance in this course, concern the important question of whether the effects of one factor, the effects of one independent variable, are relatively constant or are affected by other factors, by the other independent variables. We will see exactly what this means in our example. So what can we do when we have more factors? One possible thing would be to analyze separately for each factor, so each independent variable taken into consideration separately, independently, using one-way ANOVA. This still allows us to account for multiple categories or groups within that factor. Let's work with an example. In this example, with real data from 577 children, we will have two independent variables, one being grade, so there are children in grades 2, 3, and 4, and the other independent variable will be sex, so there are girls and boys. And the dependent variable of interest is reading comprehension, is the number of correct answers to questions related to passages children read. There is a maximum of 18 questions that can be answered correctly. And the question is, are these variables related? In other words, does sex affect reading comprehension? Or stated differently, are reading comprehension scores different between girls and boys on average? And the other question is, does grade affect reading comprehension? Or stated differently, are reading comprehension scores different for kids in grades 2, 3, and 4 on average? Obviously, we expect there to be great differences between grades. We expect this independent variable to be related to the dependent variable, but we don't really have much expectation for the sex variable. So let's take them separately one by one first. This is a box plot of reading comprehension by sex. So the scores for girls versus the scores for boys. Looking at this box plot does not suggest that we should expect any statistically significant differences. If we run the t-test, we find a p-value of 0.263. So we do not reject the null hypothesis that the two means are equal and an associated very small effect size. If we run the f-test in a one-way ANOVA, we get, of course, the same p-value, and indeed the f value that we get is equal to the square of the t value. So sex does not seem to affect reading comprehension if analyzed in these ways that are already familiar to us. This is the ANOVA table showing the sums of squares and mean squares. Let's now analyze the other independent variable separately, again, only by one-way ANOVA, because here we have three groups. So it is not possible to run a t-test with three groups. If we wanted to compare these with t-tests, we would have to run three different t-tests, one for each pair of grades. But we can run a one-way analysis of variance with this result, with a significant p-value, which suggests we should reject the null hypothesis that the means per grade are equal and instead conclude that there are differences between grades in reading comprehension, which makes a lot of sense. If we take a look at the ANOVA tables, we can remind ourselves that the F ratio is not a proportion, it's actually just a ratio. So we divide the mean squares associated with our factor by the mean squares associated with the residual or the within error variance to get the F ratio. And we do the same thing in each analysis. So it's a ratio of quantities associated with variability in the data. If we want to look at the corresponding effect sizes, then these aren't just ratios, but are actual proportions of variability in the data, proportions of the total sum of squares. Remember that each ANOVA table lists the sums of squares such that if you add them all up, you come up with the total sum of squares in the data, the total sum of squares associated with just a single mean. So obviously, if you add these numbers, these two numbers, you should get the same total as when you add these numbers, because these are both analyzing the same data. They're just split up by a different grouping, but the total variability present in the data is the same. The total sum of squares is the same. It is just split up differently depending on how much of the variability is taken up by the grouping. And the effect size is an actual proportion of the total variability present in the data that is accounted for by this specific grouping. So 18 over the total is this minuscule proportion, practically nothing accounted for by sex in the reading comprehension data. 977 over the total is actually almost 12%. Almost 12% of variability in this reading comprehension test is accounted for by grade. That really leaves a lot to individual variability between children. So that's how we can look at the effects of these two independent variables separately in two separate analyses. We already knew how to do that. But we want to ask more questions. The separate analyses don't really let us compare effects or see one effect in the context of the other factor. In order to be able to do that, both effects have to be taken into account simultaneously. So we need a way to have both independent variables in at the same time. If we split the data by both groups simultaneously, we can see that they're something like this. So these are girls in grade 2, boys in grade 2, girls in grade 3, boys in grade 3, girls in grade 4, boys in grade 4. We can see that there doesn't seem to be any effect of sex here or here. We're not so sure here, maybe. There might be an effect here based on these box plots. So there is a question mark. Maybe sex has a difference in grade 2, but not later. We can see, of course, that there seems to be an effect of grade. So these scores are lower than these scores, which are lower than these scores. So there's probably an effect of grade. We already know it exists, but now I'm commenting on this new graph. When we have more than one independent variable, this kind of graph can become difficult to interpret. Although box plots are always important, and we should always look at them first because we have a better idea of how the data are distributed. So we can actually see the middle half of the data. However, we usually then turn to graphs like these in which we represent statistics. So this represents the distribution of the data non-parametrically by the quartiles, whereas this kind of graph represents the means typically and some measure of the standard error of the mean, such as a confidence interval or a least significant difference on something like that using an error bar. So these are the means. These don't tell you anything about the rest of the distribution. But you can see from this type of graph that the means between sexes are essentially the same for grades 3 and 4, but possibly not the same for grade 2, although the intervals are overlapping. So we don't know what is going on here. We also see that there is a trend for increasing scores, mean scores with grade. So that's a different way to visualize the data when we have two independent variables. This is a very common one and one that we will need, but it is a dangerous one to look at first because it hides the properties of the distribution. At any rate, these are important numbers because the analysis of variance actually tests equality of means. So it is this information that we're looking at now that is relevant for the ANOVA. Let's see what the analysis of variance looks like by entering both independent variables together. I am not going to show you how that's calculated. It gets fairly complicated and we have no time to deal with it. It is also not very useful because it doesn't really change the concept of splitting the sums of squares. The difference is that now there are more parts to the total sums of squares because there are more factors that can account for variability in the data. Let us first look at what is called main effects. Main effects are the average effects of each factor. Here we have two independent variables, so sex and grade. These are our two factors in the analysis of variance. Each factor gets its own row, and the row associated with each factor displays information that concerns the average effect of this factor. What this means is that these things here are on average for all grades. And these things here are on average for both sexes. The total of all of these sums of squares is the total sum of squares, which is all the variability that's present in these data. And in order to test specific hypotheses about each factor, we have to divide the corresponding mean squares. So if we want to answer the question whether there are differences between the means for the two sexes, then we have to divide this mean square here as mean squares between for this factor to the residual mean squares here, that's mean squares within, for the whole table, so the unaccounted part of the variance, and that's the ratio. That's the F value, and the associated P value is not statistically significant. So on average, there is no effect of sex on reading comprehension. In other words, there is no difference in the mean reading comprehension score for boys and the mean reading comprehension score for girls. These two means are not statistically significantly different, or they are statistically indistinguishable. Turning to the second factor, the main effect of grade is shown here if we divide these mean squares between by, again, the residual mean squares we come up with this F ratio and the corresponding p-value, which is a very low p-value. In fact, the difference between grades is statistically significant. This means that the average reading comprehension score for grade 2, grade 3, and grade 4 are not all equal. This doesn't tell us which grade or grades are not equal on average to which others. It tells us that the 3 means associated with the 3 grades are not all equal. And this is a statistically significant difference. So these are the main effects. Again, the main effects for each of the factors are the average effects. This is the main effect of grade, which holds on average for boys and girls. But the interesting thing about entering all these independent variables together is that we can actually look at what is called a statistical interaction. The statistical interaction asks whether the effects of one factor are affected by the other factor, or are they constant? And different way to say this is, are the effects of one factor different at different levels of the other factor? Let's see what this means in our example. Are the reading comprehension differences between grades different for girls and boys? That's one way to ask the question. The differences between grades. The differences between grades is the effect of grade. Are these differences the same for girls and boys? That asks if the effect of grade is the same over the 2 levels of sex. In practice, this could ask whether boys or girls have more of a developmental increase in reading comprehension scores. Maybe boys' scores increase more between grade 2 and 4 than girls' scores, or vice versa. If that were true, then the effect of grade for boys would be different than the effect of grade for girls. Equivalently, we can ask whether the reading comprehension differences between girls and boys differ at different grades. So the difference between girls and boys, is it constant? Is it the same in grade 3, grade 2, and grade 4? Or is there a greater difference between sexes in some grades than in other grades? These two phrasings are mathematically equivalent. If the answer to one of them is yes, then the answer to the other one is yes too, necessarily. Although we may be interested in only one of these from a theoretical standpoint, statistically, it makes no difference because they are the same question. We can still phrase it in the way that we care. It's not necessary that we ask both. But there's only one thing to be tested from a statistical point of view, and that is the extent to which the main effects of the 2 independent variables do not account for all the systematic differences in our data, for all of the variability in our data. Is there something more that we can account for by considering both independent variables together? Remember, this is our display of the data, and here it looks like there might be a difference between sexes in grade 2, probably almost certainly no difference in the other grades. If that were statistically significant, then that would amount to a statistically significant interaction. If the result is statistically significant, then that would mean that the difference between sexes in grade 2 is not the same as the difference between sexes in grade 3, for example. So if that were statistically significant, it would be a significant interaction. The effects of one factor would be different at different levels of the other factor, or the effects of one factor, namely sex, would be affected by the other factor, namely what grade we're talking about. So that's the extra line in our ANOVA table right here, and we have a mean square to be divided over the residual to get an F ratio and the associated p-value, which is very large, so the interaction is not statistically significant. This means we cannot reject the null hypothesis. What is the null hypothesis for the interaction? It is that the effects of each factor are the same across all levels of the other factors. That's the null hypothesis for the interaction. The null hypothesis for the interaction is that the differences between sexes are the same in every grade. The other way to say the same null hypothesis is that the differences between the 3 grades are the same for girls and boys. That's the null hypothesis for the interaction. And because we have a large p-value, we cannot reject this null hypothesis. So it means that indeed the differences between grades are the same for both sexes, and the differences between boys and girls are the same between the 3 grades, as far as this data set is concerned. The ability to test for interactions is really the strongest point for analysis of variance, and the main reason that we choose to use it, because it allows us to get into more detail in our data and see patterns of differences that cannot be understood by looking at each factor separately. In this ANOVA table, where we have the same total variability, of course, if we add all these up, that's the total sum of squares in our data, there is a certain amount of variability which is accounted for by considering sex and grade together. And that's beyond accounting for variability just by the group means of sexes and the group means of grades. So there is a bit of sum of squares that corresponds to variability resulting from combining knowledge about sex and grade by assuming that boys in grade 2 has something to say, is in some way possibly different from saying girls in grade 2 or from boys in grade 3 or boys in grade 4. So we can calculate a sums of squares component that depends on combinations of levels of the 2 factor rather than just levels of 1 factor. What about effect sizes? The effect sizes tell us the proportion of variability in the data that can be accounted for by each factor or combination of factors. So here, the effect size for sex is the sums of squares for sex, for the main effect of sex, divided over the total sums of squares. That's very, very small. The effect size for grade is the sums of squares for grade divided by the total sums of squares, which is about 12%. Note that the results, including the F ratios and the effect sizes, are very similar, but not identical to those we got for the 2 individual analyses when we ran one analysis for sex and a separate analysis for grade. These are not identical because now we take one into account when calculating the other. Most importantly, in this case, they're very similar because there is no significant interaction. So results can change if you use independent variables together in one analysis compared to when you examine them separately. And that's, of course, the power of doing the analysis of variance with all independent variables together. Be careful with using too many independent variables because the interpretation of the results gets quickly very complicated when you have more than 2 or maximum 3 independent variables. The effect size for the interaction can be calculated in the same way as for the main effects. After all, it's just another component of the sums of squares. So divide this by the total and we get a tiny amount, a tiny proportion of variability, which is of course not statistically significant. So these are the effect sizes for our 3 rows in the ANOVA table. The interaction does not really account for any variability in our data. This way of calculating the effect size makes a lot of sense because it concerns an actual proportion of variability present in the data. But is not the only way we can use to calculate an effect size. We may be interested only in the proportion of variability that relates to each specific effect, so that effects may be comparable to different studies or different designs. A common way to look at effect sizes in analysis of variance is to calculate what is called a partial eta square. And a partial eta square only concerns the part of the sums of squares that is related to what we're looking at. So 16 here would not be divided by the total sum of squares, but only by the sum of itself and the residual. So that's the part of the variability in the data that is not related to any other factor. The variability in the data that is accounted for by other factors is excluded from the calculation of this effect size. So the proportion of variability in the data not accounted for by any other factor is the partial eta square for sex. And in the same way, we can calculate the partial eta square for grade and the partial eta square for their interaction. In this particular case, the eta squared and partial eta square are almost the same. They're equal to 3 decimal places because the effects of sex and interaction are so small that are almost 0 and are drowned by the effect of grade, which is very substantial. So the partial and non-partial doesn't make much of a difference. In other cases, there could be very large differences in these two kinds of indices of effect size, and we have to be careful when reading or reporting results using these to make sure we identify which one is being reported. Note also that eta square, the original one, is an actual proportion of total variability. So all of the eta squares together added up can never exceed 1. You cannot account for more than there is. However, the partial eta squares only consider variability not accounted for by other factors. So these can, in some instances, exceed 1, depending on how large parts of variability you exclude from the individual calculations. The general point is that these two indices mean different things, and we need to know which one we're dealing with each time. Finally, a very important issue with analysis of variance, as with other parametric hypothesis tests, is the assumptions that go into the analysis, the mathematical presuppositions that result in our ANOVA table and make it interpretable. What is assumed? What it lies behind this calculation? So the assumptions that are important for the analysis of variance, first of all, is independence. Our data should not depend on any other data values. In this case, this is satisfied because it's different children who are tested with the reading comprehension test. So these are independent. In cases where we have repeated measures, that is measuring the same child more than once or having otherwise systematically related data, like we had in the paired samples t-test, then there are different versions of ANOVA that can be used. If there are other kinds of dependencies in the data, then the ANOVA cannot be used. The second assumption is normality. Our data must be normally distributed. And this is checked as usual with tests like the Shapiro-Wilk. There are other tests that are similar. If our tests violate the assumption of normality, then if we want to run a one-way ANOVA, there is a non-parametric option for that. So there is a different test that doesn't depend on this assumption that can be used. However, if we have more than one factor, there is not much we can do because there aren't any non-parametric options for interactions. That's because interactions, by definition, critically depend on the scales of the effects, depend on effects being smaller or larger than other effects, depend on differences in means, specifically, being smaller or larger than other differences. Non-parametric tests eliminate distances in the data, essentially turning them into ordinal scale by using ranks. So it's not possible to test interactions if you have eliminated the distances in the first place. That's why there aren't any non-parametric tests for interactions. So if you're interested in interactions and your data aren't normally distributed, you are possibly in trouble. If you have only mild deviations from normality, then that's probably okay because it's known that ANOVA is relatively robust to modest deviations from normality. This means that if your data aren't too horribly distributed, too horribly skewed with outliers and such, then the ANOVA results will hold, will be what you get, will be close enough to the true answer in terms of the p-value. If you have very distorted data, you will have to resort to other kinds of approaches. And the other assumption that is very important for analysis of variance is the homogeneity of variance. Homogeneity of variance means that the variances of the different groups are not different. And when we talk about groups, we refer always to the levels of the factors. And that should hold for all the factors if you have more than one. The homogeneity of variance is very important in analysis of variance because it is assumed for the calculations. You can check whether there is homogeneity of variance in your analysis by running what is called the Levene test, which is offered in every software that runs analysis of variance. If the homogeneity of variance assumption is violated and you're only interested in one-way analysis, then you can work around that because there is an alternative to the analysis that you can use that takes into account differences in variances. If homogeneity of variance is violated and you have more than one independent variable, then you need to consider different approaches because ANOVA is invalidated by the lack of homogeneity of variance.